TON 618, abbreviation of Tonnenschindler 618, is a hyperluminous, broad absorption line, radio-loud quasar, and Lyman alpha blob located near the border of the constellations Canes Venatici and Coma Berenices, with the projected comoving distance of approximately 18,200,000,000 light-years, 107 sextillion 16 quintillion miles, from Earth. It contains one of the most massive black holes ever found, at roughly 40,700,000,000 m, or 178 duodecillion 344 undecillion pounds. As quasars were not recognized until 1963, the nature of this object was unknown when it was first noted in a 1957 survey of faint blue stars, mainly white dwarfs, that lie away from the plane of the Milky Way. On photographic plates taken with the 27.6-inch Schmidt telescope at the Tonnenschindler Observatory in Mexico, it appeared decidedly violet, and was listed by the Mexican astronomers Braulio Iriarte and Enrique Chavira as entry number 618 in the Tonnenschindler catalog. In 1970, a radio survey at Bologna in Italy discovered radio emissions from TON 618, indicating that it was a quasar. Marie Helena Ulrich then obtained optical spectra of TON 618 at the McDonald Observatory, which showed emission lines typical of a quasar. From the high redshift of the lines, Ulrich deduced that TON 618 was very distant, and hence was one of the most luminous quasars known. As a quasar, TON 618 is believed to be the active galactic nucleus at the center of a galaxy, the engine of which is a supermassive black hole feeding on intensely hot gas and matter in an accretion disk. Given its observed redshift of 2.219, the light travel time of TON 618 is estimated to be approximately 10,800,000,000 years. Due to the brilliance of the central quasar, the surrounding galaxy is outshone by it and hence is not visible from Earth. With an absolute magnitude of -30.7, it shines with a luminosity of 40 duodecillion watts, or as brilliantly as 140 trillion times that of the Sun, making it one of the brightest objects in the known universe. Like other quasars, TON 618 has a spectrum containing emission lines from cooler gas much further out than the accretion disk, in the broad line region. The size of the broad line region can be calculated from the brightness of the quasar radiation that is lighting it up. Schemmer and co-authors used both NV and SIV emission lines in order to calculate the widths of the H-beta spectral line of at least 29 quasars, including TON 618, as a direct measurement of their accretion rates and hence the mass of the central black hole. The emission lines in the spectrum of TON 618 have been found to be unusually wide, indicating that the gas is traveling very fast. The full-width half maxima of TON 618 has been the largest of the 29 quasars, with hints of 23,487,831 miles per hour speeds of infalling material by a direct measure of the H-beta spectral line, indication of a very strong gravitational force. From this, the mass of the central black hole of TON 618 has been estimated to be at 66 billion m, or 289 duodecillion 212 undecillion pounds. This is considered one of the highest masses ever recorded for such an object, higher than the mass of all the stars in the Milky Way galaxy combined, which is 64 billion m, or 280 duodecillion 448 undecillion pounds, and 15,300 times more massive than Sagittarius A*, the Milky Way's central black hole. With such high mass, TON 618 may fall into a proposed new classification of ultramassive black holes. A black hole of this mass has a Schwarzschild radius of 1,300 astronomical units, 120,900,000,000 miles, which is more than 40 times the distance from Neptune to the Sun. A more recent measurement in 2019 by Jay and colleagues, which utilizes the CIV emission line, an alternative spectral line to H-beta, using the same data reproduced by the earlier paper by Schemmer, found a lower relative velocity of the surrounding gas of 6,176,181 plus or minus 1,892,448 miles per hour, which indicate a lower mass for the central black hole at 40,700,000,000 m, consequentially lower than the previous estimate. The nature of TON 618 as a Lyman alpha emitter has been well documented since at least the 1980s. Lyman alpha emitters are characterized by their significant emission of the Lyman alpha line, an ultraviolet wavelength emitted by neutral hydrogen. Such objects, however, have been very difficult to study due to the Lyman alpha line being strongly absorbed by air in the Earth's atmosphere, limiting study of Lyman alpha emitters to those objects with high redshifts. TUN 618, with its luminous emission of Lyman alpha radiation along with its high redshift, has made it one of the most important objects in the study of the Lyman alpha forest. Observations made by the Atacama Large Millimeter Array (ALMA) in 2021 revealed the apparent source of the Lyman alpha radiation of TON 618. An enormous cloud of gas surrounding the quasar and its host galaxy. This would make it a Lyman alpha blob, LAB, one of the largest such objects yet known. LABs are huge collections of gases, or nebulae, that are also classified as Lyman alpha emitters. These enormous, galaxy-sized clouds are some of the largest nebulae known to exist, with some identified LABs in the 2000s reaching sizes of at least hundreds of thousands of light-years across. In the case of TUN 618, the enormous Lyman alpha nebula surrounding it has the diameter of at least 330,000 light-years, 1,940,400 trillion miles, twice the size of the Milky Way. The nebula consists of two parts: an intermolecular outflow and an extensive cold molecular gas in its circumgalactic medium, each having the mass of 50 billion m, or 219 duodecillion 100 undecillion pounds, with both of them being aligned to the radio jet produced by the central quasar. The extreme radiation from TUN 618 excites the hydrogen in the nebula so much that it causes it to glow brightly in the Lyman alpha line, consistent with the observations of other LABs driven by their inner galaxies. Since both quasars and LABs are precursors of modern-day galaxies, the observation on TUN 618 and its enormous LAB gave insight to the processes that drive the evolution of massive galaxies, in particular probing their ionization and early development.